All right, in this video, I want to talk about section 7.8. This is what's called improper integrations or improper integrals. When we talk about improper integrals, what we mean is integrals of infinite regions. So let me explain what I mean by that. When I say infinite, what I mean is unbounded regions. So for example, you could have a function that maybe goes to 0 like this, okay, something like that. Maybe it starts at some value a, and then you want to talk about what is this area under here. And even though this value it goes to infinity, it's unbounded. Bounded means that you can take, so a set, just explain my terminology here. A set is bounded if you can find some circle that contains it. A set is unbounded if there is no circle that contains it. And so in this case, it doesn't matter how big the circle is. The implication is that this function will asymptote to 0 for forever. X can be as large as you want. So there's no one circle that contains the region. So even though the region is unbounded, we can still talk about whether or not this area is finite or not. Okay, and so there's a few different types of improper integrals, but this is the first one where you have this region that goes to infinity. And so here's how we're going to deal with this. If we integrate this function, let's just call this f. If we integrate this function f from a to infinity, the way that we're going to think about this is as the following limit. This is going to be the limit as t goes to infinity of the definite integral from a to t f of x dx. Okay, that's the way I like to think about this. I think the book uses capital N instead of t, but whatever. So this is going to be the limit of definite integrals. And then as t gets larger and larger, either one of two things is going to happen. Okay, so if this limit as t goes to infinity of our integral exists and is finite, so if this limit exists and equals 5 or something, then we say that this integral f, let's say that this limit exists and it equals some value L. Let's just write it that way. If this limit equals L for some number L, doesn't have to be positive or negative, it doesn't matter. But if this limit is equal to L, where L is some finite number, then we say that this integral converges to L. Okay, so that's a new word for us. So this integral converges to L. Okay, otherwise, so if this limit doesn't exist, so if the limit from the integral from a to t of f of x dx does not exist or is infinite, then we say that this integral from a to infinity diverges. Sometimes you'll hear some people say that this integral diverges to infinity. What that means is that this limit was infinite. So it diverges because it's infinite, because it's infinity. Okay, so that's the main thing from this section. That's it. If we have improper integrals, we can think of them as limits of definite integrals. Yeah, so if we have improper integrals, that's limits of definite integrals. We can compute these limits, figure out if we get a number or not. If we get a number and the number is like 5 or 102 or whatever, we're going to say that the integral converges to that number. If this limit doesn't exist, or if this limit's infinity or minus infinity, we say that the integral diverges. Okay, so the two new words that we're introducing here, converges and diverges, as far as these improper integrals. And I think the best way to do this is just with examples. Okay, let's think about some examples here. So let's look at the integral from 1 to infinity of 1 over x squared dx. And this is going to be the limit as t goes to infinity of the integral from 1 to t, 1 over x squared dx. This we can evaluate, no problem. This is actually a Calc 1 integral. And so we get the limit as t goes to infinity. The antiderivative of 1 over x squared is negative 1 over x. We're going to evaluate that from 1 to t. And when we plug in t, we're going to get, let's see, negative 1 over t. When we plug in 1, we're going to get minus negative 1 over 1. And so that's going to be the limit as t goes to infinity of 1 minus 1 over t. And as t goes to infinity, the 1 over t vanishes to 0 and our limit is 1. And so it turns out that this integral of 1 over x squared from 1 to infinity is equal to 1. Okay, and so what this means is that if I take this 1 over x squared, which could very well have been the graph that I had before, right? It has the same shape anyways. The integral from 1 to infinity, even though this region is unbounded, okay, my arrow got in the way of the graph here, but even though this region is unbounded, the area under this region gets small enough, quickly enough, that it never gets above 1. Okay, this limit is going to be 1. Okay, and so that's the first example. So this converges to 1. Let's look at the integral of 1 over x squared of 1 over x. Same idea, write this as a limit. So this is a limit from 1 to t, integral from 1 to t of 1 over x dx. And we know how to integrate this as well. This is going to be the natural log of the absolute value of x evaluated from 1 to t. And so that's going to be the limit as t goes to infinity of the natural log of t minus the natural log of 1. I can just assume t is positive because t is going to infinity. And so that's going to be the limit as t goes to infinity of the natural log of t, because the natural log of 1 is 0. And we know that the natural log goes to infinity as its argument goes to infinity. And so this is going to be infinity. And therefore, that tells us that this original integral diverges. Okay, so even though this integral also goes to 0, okay, basically the same way, it doesn't go to 0 quickly enough that we capture all of the area. The area gets as big as we want it to be. Okay, and so this area here is going to be an infinite area. It's a region with an infinite area. So this integral diverges. So that's interesting somehow that 1 over x diverges, but it kind of barely diverges in a way, and 1 over x squared converges. And so let's try and figure out where that dividing line is. And let's look at, I don't care about what it converges to or not. Let's look at 1 over x to the p, where p is some power. So we've done 1 over x squared. We've done 1 over x to the first. Let's do 1 over x to the p. And this is going to be the limit as t goes to infinity of the integral from 1 to t. So that's fine. We know what happens when p is 1. We know that this diverges. So we already can kind of write this down and set that aside. This diverges if p is 1. The reason why I care what happens with p is 1 is that this is the only value of p where the antiderivative is not going to use the power rule. Right? We know if p is 1, we get the integral of 1 over x, which is involves logs. Otherwise, it involves the power rule. So if p is not equal to 1, so here I'm using that p is not equal to 1, our integral is going to be, so this is x to the negative p. We're going to add 1 to the exponent. So it'll be x to the negative p plus 1 divided by negative p plus 1. And we're going to evaluate this from 1 to t. And so this is going to be the limit as t goes to infinity of t to the 1 minus p over 1 minus p minus 1 over 1 minus p. Okay, this is some finite number. When p is not equal to 1, this is just some number. And therefore, it's not going to affect the convergence or divergence, right? If this is going to go to infinity, then the whole thing goes to infinity. If this goes to 5, then the whole thing goes to whatever, 5 minus 1 over 1 minus p. And so, you know, if this converges, then so does the whole thing. If this diverges, so does the whole thing. So really, we just have to look at this t to the 1 over p, t to the 1 minus p. And so let's think about when that's going to go to 0 and when that's not. So this is going to go to negative 1 over 1 minus p if p, so remember, it's the exponent is fixed but we're letting the base t go to infinity. And so if we have a positive exponent, then this is going to go to infinity. So that happens if 1 minus p is positive. If we have a negative exponent, okay, then this is going to go to negative 1 over 1 minus p. And we know that if p is equal to 1, we also know what happens, right? We know that this integral diverges because we just did that. And so it turns out that this is going to converge. So this converges. And by this, I mean the integral from 1 to infinity of 1 over x to the p converges if 1 minus p is less than 0, or in other words, p is greater than 1. And this integral diverges if 1 minus p is greater than 0, or p is less than 1. And then one other thing that we know that this diverges if p is equal to 1. So we can add that in. We get that this is we get the p equals 1 for a different reason, but we might as well just incorporate it all together. So therefore, this integral from 1 to infinity of 1 over x to the p converges if and only if. So if and only if p is strictly bigger than 1. Okay, so when I say if and only if, I mean it goes both ways. So it converges if p is bigger than 1, and it diverges if p is less than or equal to 1. Okay, so this is a really famous integral that we're going to use over and over, actually, in this section, but also in chapter 11. So we'll see this actually has some relevance when we're going to talk about stuff in chapter 11. Okay, but that's that integral for now. The next type of integral that I want to look at, the next type of improper integral, is not one where the region, the interval goes from like a to infinity, but maybe we have a finite interval and we're looking at something like the integral from 0 to 1 of 1 over square root of x. So maybe we have a discontinuity. In other words, a vertical asymptote at some value. So for example, if we look at 1 over square root of x, we know at 1, it's going to be 1, and then it blows up at 0. Okay, and so maybe the region's unbounded because we have a discontinuity of the function, right? And therefore a vertical asymptote, and it blows up, goes to infinity. So this is another one. And this is actually an integral that if you didn't know this was an improper integral, you could actually do this the wrong way and get the right answer, which just happens sometimes. So that's kind of nice, actually, if we do it the wrong way and get the right answer. But what would happen here is we're going to think about this as the limit of t going to 0 from the right of the integral from t to 1. So we have to kind of think about where's the discontinuity going to occur, and then that'll be the value that we put in for the limit. Okay, so here we're letting t go to 0 from the right because we don't care about what happens for negative values. In fact, square root of x doesn't make any sense for negative values, so we can't even think about it there. Anyways, so this is the limit that we're going to look at. And this is going to be the limit as t goes to 0 from the right. If we have 1 over square root of x, that's x to the negative 1/2. The integral is going to be x to the 1/2 divided by 1/2. So that's 2 square root of x. Evaluate that from t to 1. And that's going to be the limit as t goes to 0 from the right of, let's see, 2 times square root of 1 minus 2 times square root of t. And as t goes to 0 from the right, square root of t goes to 0, and you get 2. Okay, so that tells you that this integral converges. And it converges to 2. Okay, so that's another type of these. Let's look at the integral from 0 to 1 of the natural log of x. Okay, so this is going to be the limit. Again, natural log has a discontinuity at 0. The natural log is going to look like, so the natural log looks like that. We're going to go from 0 to 1. And so therefore, we're going to be talking about this area. So if the integral converges, it's got to be negative because it's below the x-axis. The question is whether it's finite or infinite. Okay, so this is going to be the limit as t goes to 0 from the right, the integral from t to 1, the natural log of x dx. And whether you remember this integral or whether you have to do this using integration by parts, either way is fine. This is going to be the limit as t goes to 0 from the right of x natural log of x minus x. We're going to evaluate that from t to 1. When we plug in 1, what's going to happen is that we're going to have 1 times natural log of 1. So that's 0, minus 1. And then minus the quantity t natural log of t minus t. And so, of course, the natural log of 1 is 0, so that piece is gone. So this is the limit as t goes to 0 from the right of negative 1 minus t natural log of t plus t. And so, again, all we have to figure out is whether this is infinite or not. All that's really going to matter here is this middle term. If this middle term goes to infinity or negative infinity, then the integral diverges. Otherwise, the integral converges. And here, this t is going to go to 0. So we don't even really need to worry about it. So this is going to be the limit. Let me just formally write what we're going to do here. This is the limit of negative 1 plus the limit as t goes to 0 from the right of negative t natural log of t. In fact, I can do one better and we can just move the negative outside. And then plus the limit as t goes to 0 from the right of t. And so, of course, this first piece is negative 1. This last piece is 0. All that matters is this middle piece. So let's look at that. So we have the limit as t goes to 0 from the right of t times the natural log of t. And guess what? That's an indeterminate limit. And so what we're going to have is we're going to have 0 times infinity. So that's indeterminate. And so we're going to have to somehow use L'Hopital's rule, which means somehow we need a fraction. And so hopefully by now it's comfortable enough, this trick. We're going to take the natural log of t divided by 1 over t. And so now we have a fraction. We can apply L'Hopital's rule, and we got the limit as t goes to 0 from the right of, we get infinity, negative infinity over infinity. So we can apply L'Hopital's rule. Natural log of t differentiates to 1 over t. 1 over t differentiates to negative 1 over t squared. And then if I don't think about this, I get infinity over infinity again. But if I do think about this, we could multiply by the reciprocal of the denominator. And that's just going to be the limit as t goes to 0 of negative t, which is again 0. And we didn't do anything fancy to this. This wasn't the log of anything that we were looking at. This limit is just 0. And so altogether, this is going to be negative 1 minus 0 plus 0 or minus 1. And so it turns out that this area under the natural log of x from 0 to 1 is going to be finite. This happens to be minus 1. This integral is negative 1, meaning that the area under the curve is 1. Okay, and so that's that type of problem. Just one more to talk about. If we were to do the integral of 1 over, say, x squared from 0 to 1, this is going to be the same limit as t goes to 0 from the right, integral from t to 1, 1 over x squared dx. And we know how to deal with this. This is the limit as t goes to 0 from the right of negative 1 over x. We're going to evaluate from t to 1. And that's going to be the limit as t goes to 0 from the right of negative 1 plus 1 over t. And the problem here is that as t goes to 0 from the right, 1 over t blows up to infinity. And this limit's going to be infinity. And so this integral, it turns out that this integral diverges. You can check that the integral of 1 over x to the p dx diverges if p is greater than or equal to 1. Okay, and it happens to converge otherwise. This is a different integral than we had before. Even though the integrand is the same, the bounds are different, and that matters a lot. Okay, so this is, I think, another good fact to know. The other p integral is the more important one. We're going to use this one over and over and over and over in chapter 11. Okay, the other one is just kind of a nice thing to know as well. Okay, so that diverges if p is greater than or equal to 1. So the last thing I want to do in this section, okay, so the last thing I want to do is, rather than me giving you an integral and you telling me whether or not what it converges to or whether it diverges, all I want to know is, does it converge or does it diverge? And I don't care about the value that it converges to if it converges. So what I want to do is I want to look at the integral from 1 to infinity of 1 over x squared plus x dx. Okay, and I want to think about, does that converge or diverge? And we're going to be able to use two things here. And these are facts that, are kind of obvious and get taken for granted. But if you have the integral of a function f, let me frame it a little better. Say we have two functions f and g. And let's say f is greater than or equal to g on some interval from a to b. If that's the case, then the integral of f is going to be greater than or equal to the integral of g. Not a shocking statement there, right? If I have two functions, say f and g, and I integrate them from a to b, let's give them color so they're a little easier to look at. So we have g and f. Then the area under the green curve is going to be more than the area under the orange curve. Okay, not shocking. The same is true actually, whether the function's above or below the x-axis, it's the same calculation. So what I want to do is I want to apply that to these integrals. And so if I look at the integral from 1 to infinity of 1 over x squared plus x, I'm going to do this very carefully the first time. And then we'll see how this works in general. But this, just by definition, is an improper integral. So the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus x. I could actually, if I felt like it, evaluate this integral by doing a partial fraction decomposition. And if you want to figure out exactly what this integral equals, that's fine. It's just a good starting example for us. So we're going to have 1 over x squared plus x integrated from 1 to t, and we're taking the limit as t goes to infinity. And so what I want to do is, instead of actually evaluating the integral, I just want to be able to kind of look at it and figure out, does it converge or does it diverge? That turns out to be a really useful skill, especially when we get to chapter 11. So that's what I want to do. Okay, so here's the way that we're going to think about this. When x is large, the dominant term in the denominator is going to be the x squared. So even though x goes to infinity when x is large, all that's really going to matter is this x squared. And so we can basically drop all the non-dominant terms. There's kind of two ways that we can do this. And I'll walk through both of them very carefully with you, but we can drop the non-dominant terms, and then that's going to tell us the behavior of the integral. So in the way that I just described, that actually doesn't involve inequalities. That just involves knowing that 1 over x squared plus x is going to be about the same as the integral. It's not equal to, and I don't actually care about how close this is. But this is going to be about equal to the integral of 1 over x squared. Okay, because when x gets large, the 1 over x squared plus x is basically 1 over x squared, right? When x is a million, this is going to be a trillion plus a million, which is basically a trillion. So even though a million is huge, just in comparison, it's nothing. So this converges. And if they're approximately equal to each other, that means that, if one's 5, the other's 7 or something, right? I don't care how close they are, but if one's finite, the other's finite. Okay, so this, it turns out, converges. So that's one way to do this. Another way to do this is to use this inequality method that I talked about over here. Okay, so if we look at these inequalities there, what I want to do is I want to compare 1 over x squared plus x to something that we know a lot about. In our case, 1 over x squared. And we know that x squared plus x is greater than x squared. And therefore, 1 over x squared plus x is less than 1 over x squared. So this entire limit is going to be less than or equal to the limit as t goes to infinity of 1 to t 1 over x squared dx, which is the integral from 1 to infinity of 1 over x squared. And again, this converges, and that tells you that the original integral converges too. Okay, so this integral converges, and we've kind of given 2 reasons for it. Okay, so that integral converges. And so I want to be able to just kind of look at an integral and you tell me whether or not you think this integral converges or diverges. Okay, that's a very useful skill to have here. So let's integrate 1 over the integral of x cubed plus 4, and we're going to evaluate this from 0 to infinity. Okay, and so I want to think about, does this integral converge or diverge? And I have to be a little bit careful here. When we have 2 potential problem spots. When x is large, okay, so if x is large, then 1 over x cubed plus 4 is going to be approximately 1 over x cubed. Okay, those squiggles don't mean anything in particular, just approximately they're equal. And that's true, but that's not true when x is small. And the problem is that when x is small, 1 over x cubed has a discontinuity at 0, but this original integral does not. And so what we can do is we can break this up into the integral from, say, 0 to 1, or 0 to whatever number you like, I don't care, plus the integral from 1 to infinity. And what we can do for the first integral is that this is a function, it's continuous over a nice finite bounded interval. Everything is perfectly fine. It's going to be some number. It's going to be like 5. I don't know what the number is. I don't care. It's going to be some number. And all we really have to look at is the second integral. And if this integral converges, then so does the sum of those 2, right? This is equal to 2 or something. If this integral is equal to 5, then the whole thing is finite. If this integral is infinite, then the whole thing is infinite. And now we can use our approximation that the integral from 1 to infinity of 1 over x cubed plus 4 is approximately the integral from 1 to infinity of 1 over x cubed, okay, which converges. So it tells us that this original integral converges too. We could go through and very carefully do the inequality business, and if you prefer that, that's fine. I like to just be able to look at it and tell whether or not. The last one I want to look at is, let's look at this integral from 1 to infinity of 1 plus sine squared of x over x. Okay, and here an inequality is going to be very useful. It turns out that 1 plus sine squared is greater than or equal to 1, because sine squared of x, it's squared, it's always greater than or equal to 0. And therefore, this integral is going to be at least as big as the integral from 1 to infinity of 1 over x dx. But this integral diverges. And so if the original integral is at least as big, and if this integral goes to infinity, then the original integral also goes to infinity. And so we can argue that way that this original integral diverges too. So this integral diverges. I want to be very careful about what I just showed there, because it's easy to convince yourself of some things that aren't true. So here's what I want to say. Here's how we use that inequality statement in a precise way for these improper integrals. If the integral from a to b of a function, and I don't actually care if it's whatever, a to infinity. Let's just do it that way, because that's going to be the scenario where we're going to use this later in chapter 11. But if this integral is less than the integral from a to infinity of g of x, then we know the following. We know that if the integral of g converges, and let's say, by the way, let's just say that everything is positive. Otherwise, this isn't true. But if the integral of g converges, then so does the integral of f. Then that integral converges. On the other hand, if this integral is greater than the other integral, and if the integral of f diverges to infinity, well, if it diverges, then the integral of g diverges. Okay, and that should be reasonable, right? That should be hopefully at least a little bit intuitive. If you have some integral and it's less than or equal to 5, then this integral converges. And on the other hand, if you have two integrals and you know that this integral goes to infinity and this integral is greater than that, then that integral also goes to infinity. That's the intuition there. However, you have to be very careful to apply this correctly. If you know that this integral is less than or equal to infinity, you know nothing, right? You don't know if it's infinity. You don't know if it's 2. You know absolutely nothing. So if you know that the integral of g diverges and the integral of f is less than or equal to it, you still have no idea about the integral of f if it converges or diverges. Okay, to say that something's less than or equal to infinity means it could be anything. Okay, you just don't know. So just be careful about how you apply this rule in each of these cases. But otherwise, that's all I wanted to say about this. And again, this is a very useful skill. I know it seems a little bit silly to look at an integral and tell whether or not it converges or not. It turns out to be a very useful skill for some of the things that we're going to do in chapter 11. Okay, and we'll talk about that much later.